Students, in this session we are going to see classification of magnetic materials. So as I told already, magnetic materials are classified as diamagnetic, paramagnetic and ferromagnetic. First of all, we are going to see what are diamagnetic material. So in this magnetic material, all magnetic material is made up of atoms. And inside the atom, the electrons are revolving around the nucleus. Due to the orbital motion of the electron, orbital magnetic moment is developed perpendicular to the plane of the orbit. So, the magnetic moment developed due to the orbital motion of the electron is always perpendicular to the plane containing orbital motion of the electron. So when you consider an atom is having large number of electrons. All the electrons do not have the same orbit. So the orbits are randomly oriented. So because several electrons are having different orbital motion in different plane, the magnetic moment produced due to the orbital motion of the electron is also oriented in random direction. As a result, the resultant magnetic moment is the vector sum of all the magnetic moment due to the orbital motion of the electron. So when you find vector sum, the resultant magnetic moment is 0 in the case of diamagnetic material. So, in a diamagnetic material, no individual atom is having resultant magnetic moment. First one. When such a magnetic material is kept in a uniform magnetic field, so when such a magnetic material is kept in a uniform magnetic field, the magnetic moment developed or induced due to the external magnetic field. This magnetic moment produced due to the external field speed up the electron. Some electrons get speed up and they will produce which electrons are speed up, and some electrons get speed up and some electrons slow down by the external magnetic field. So according to Lenz's law, those electrons which are anti-parallel to the external magnetic field, they get speed up. So they will produce magnetic moment opposite to the magnetizing field, external magnetic field. As a result, what will happen? This magnetic material will get a force which will make the magnetic material to move from stronger region to the weaker region. So when it is kept in non-uniform magnetic field, so this magnetic material will experience a force which makes the magnetic material to move from stronger region to the weaker region. It means that these diamagnetic materials are repelled by the external magnetic field. So initially net magnetic moment is 0. When they are kept in uniform magnetic field, some electrons are speed up and some electrons are slowed. The speed of electrons will produce magnetic moment opposite to the direction of the external magnetic field. When such a diamagnetic material is kept in non-uniform magnetic field, this diamagnetic material, due to the induced magnetic moment, it will experience a force which will make the diamagnetic material to move from stronger region of the external field to the weaker region. So for example, for diamagnetic material are bismuth, copper, water, etc. So these are the examples for diamagnetic material. When we consider the magnetic properties, already we have seen intensity of magnetization is very low. When you consider permeability is negative. Susceptibility is negative, is also negative. When it is kept in external field, when this material is kept in external field, field lines are repelled by the magnetic material. Susceptibility Im is independent of temperature. So these are the properties of the diamagnetic material. So example for diamagnetic material: bismuth, copper, water. Permeability is negative value less than 1. Susceptibility is also negative value less than 1. When diamagnetic material is kept in external field, the field lines are repelled by the magnetic material. Susceptibility Im is independent of temperature. So these are the properties of diamagnetic material. Next we are going to see the properties of paramagnetic material. So what are called paramagnetic material? These are the magnetic material whose atom has resultant magnetic moment. So every atom, due to the orbital motion of the electron, produces orbital magnetic moment. The spinning motion of the electron produces spin magnetic moment. The resultant magnetic moment is the vector sum of the orbital magnetic moment and spin magnetic moment. So every atom or molecule will have resultant magnetic moment. But since due to the orientation of this magnetic moment in random direction, resultant magnetic moment is 0. So once again I repeat, every atom or molecule will have resultant magnetic moment, but the resultant magnetic moment are randomly oriented. The net magnetic moment of the specimen is 0. When such a magnetic material is kept in uniform magnetic field, the magnetic moment which are randomly oriented, now they will tend to align themselves in the direction of the external magnetic field. So let us consider this be the paramagnetic material. So this is the magnetic moment of different atoms and molecules before the application of external magnetic field. But when the magnetic field is applied, all the magnetic moments will tend to align in the direction of the magnetic field. This alignment will exist as long as the external field exists. Once external field is removed, again the magnetic moment will orient in different direction. When the same paramagnetic material is kept in non-uniform magnetic field, due to the applied non-uniform magnetic field, this magnetic material will experience a force which will make the magnetic material to move from weaker region to stronger region. So in the earlier case we have seen it moves from stronger region to the weaker region. But here this paramagnetic material moves from weaker region of the external magnetic field to the stronger region. This tells that external magnetic field attracts the paramagnetic material. So what are the magnetic properties? What are the examples for paramagnetic material? Aluminium, chromium, platinum, oxygen, etc. are the example for paramagnetic material. So what are its properties? Permeability is positive and low value. So it is greater than 1, but the value is low value. What about the second property? We have seen, isn't it? Permeability, then susceptibility. Susceptibility Chi-m is depend on temperature. Chi-m is inversely proportional to temperature. Intensity of magnetization. Intensity of magnetization is positive and very large. Positive and very large. Then fourth one, in the external magnetic field, field lines are attracted by the specimen. So there we have seen in the external magnetic field, the field lines are repelled by the specimen. But here in the external magnetic field, the field lines are attracted by the specimen. So inside the specimen, now more number of field lines begins to flow through it. So these are the properties of the paramagnetic material. Once again I repeat, permeability is positive but low value. Susceptibility is dependent on temperature. Susceptibility is inversely proportional to temperature. Then intensity of magnetization is very large. External magnetic field, the field lines are attracted by the specimen. So these are the properties of the paramagnetic material. In this session we are going to see about ferromagnetic material. In the case of ferromagnetic material, every atom or molecule will have permanent dipole moment. So they have resultant dipole moment. Not only that, this dipole moment produced by the atoms or molecules will align in the same direction up to a certain region. This region up to which all the dipole moment align themselves in a particular direction is called as domain. So ferromagnetic domain. So in ferromagnetic domain, when you see all the magnetic moments align themselves in the same direction. So this type of domains are called as ferromagnetic domain. So example for ferromagnetic material: iron, nickel, cobalt, etc. So they are explained by domain theory. The theory which explains is called as domain theory. So domain is nothing but When you consider a ferromagnetic material, inside the ferromagnetic material, every atom or molecule will produce resultant dipole moment. When you see the orientation of the dipole moment, up to certain region, all the dipole moment align themselves in a particular direction. This region up to which the magnetic moment aligned in a particular direction is called as domain. When such a magnetic material is kept in an external magnetic field, then what will happen? All the dipole moments begins to align themselves in the direction of the external magnetic field. So, the domain region increases. So this produces dipole moment in the direction of the applied magnetic field. Such a magnetic materials are called as ferromagnetic material. Example, iron, nickel, cobalt are the example for ferromagnetic material. When such a magnetic material is kept in, when they are kept in uniform magnetic field, the regions of the domain gets disappear or the domains increases in size and all the magnetic moments begin to align themselves in the direction of the applied external magnetic field. When such a magnetic material is kept in non-uniform magnetic field, this magnetic material will experience a force and they are strongly attracted. So, in a non-uniform magnetic field, they will experience a large amount of force which will make them to move from weaker region to the stronger region. So, this tells that ferromagnetic materials are strongly attracted by the external magnetic field. So what are the properties of ferromagnetic material? As we see earlier, permeability is positive and very large. Very large. Intensity of magnetization is also positive and very large. In the external magnetic field, field lines are strongly attracted. Field lines are strongly attracted by the specimen. Susceptibility Km is inversely proportional to temperature and its value is given by Km is equal to C by Tc minus T. So since this Km is dependent on temperature, as the temperature increases, susceptibility also decreases. At a particular temperature, the susceptibility of ferromagnetic material decreases to paramagnetic material. So at that temperature, this ferromagnetic material will behave as a paramagnetic material. This temperature at which ferromagnetic material becomes paramagnetic material is called Curie temperature. So when a graph is plotted by taking temperature along the x-axis and susceptibility along the y-axis, this is Curie temperature and you will get a graph like this. But in the case of paramagnetic material, when a graph is plotted by taking susceptibility along the y-axis and temperature, you will get a graph like this. This is for ferromagnetic material and this is for paramagnetic material. For paramagnetic material, chi m is given by chi m is equal to C by E. This is called as Vs law and this is called as Vs Curie law. So these are the properties of ferromagnetic material. Permeability is positive and very large. Intensity of magnetization is positive and it is also very large. In the external magnetic field, lines of force are strongly attracted by the specimen. Susceptibility is inversely proportional to temperature. As the temperature increases, susceptibility goes on decreases. At one particular temperature called Curie temperature, the susceptibility of magnetic material, ferromagnetic material, become equals to paramagnetic material. So this temperature at which a ferromagnetic material is converted into paramagnetic material is called Curie temperature. The value of susceptibility above the Curie temperature is given by chi m is equal to C by Tc minus T. Tc is the Curie temperature and T is the temperature at any value. This Q is a constant which is called as Curie's constant. So these are the properties of ferromagnetic material.